I'm going to focus on GIS as an approach to interacting with data. I'll do this first by introducing fundamentals like what GIS stands for, the two main data types that GIS operates with, and some other software where you can find those, and then I'll end by introducing the concepts of georeferencing and digitizing, but in a software agnostic way. What does GIS stand for? Typically, it refers to Geographic Information Systems. Now, let's break that down so we can understand each component. Geographic means having to do with a visual representation of space. Information involves the transposition of data, which are a series of structured observations, into something that has meaning. And then there's systems, which can be a way to do a thing or how different things interact with one another. So, putting it all together, we're talking about a series of observations, data, with meaning, information, that have a spatial component, geographic, that are organized in a way so that those observations may be able to interact with one another in a standardized way, a system. But if you want the straightforward Wikipedia definition, they say that a GIS consists of integrated computer hardware and software that store, manage, analyze, edit, output, and visualize geographic data. Now that you have a couple of definitions, let's start with something that you might be more familiar with, a map. A map is a kind of geographic information visualization, similar to, at least in spirit, a data table or a chart. It takes observations and then organizes them graphically and spatially in a standardized way. However, because the information in the map is static and can't be sorted, filtered, related to, or directly linked to other kinds of data, it doesn't meet the qualifications of a geographic information system. A GIS, on the other hand, allows you to do all of those things either through a graphic user interface, aka a GUI, or through code like SQL, Python, R, and some other coding languages. This ability to select, filter, sort, etc. allows us to be able to aggregate and analyze spatial data in a way that static maps don't have the ability to do very easily. This is also where the exact steps for how to do these things will get you into the weeds of specific GIS software. When it comes to picking a graphic user interface-based piece of software, picking between Esri Arc products and QGIS is a lot like picking between the Adobe products for visual editing and their free or open source equivalents, things like Inkscape and GIMP. All of these programs work, they just have different time, energy, costs, and levels of reliability, especially if a commercial service chooses to stop supporting a specific feature or software. Because of this, I encourage people to focus on the concepts underlying GIS and spatial data rather than which buttons to click or commands to use. That's because if you understand what you're doing based on the concepts that explain why you can do it, you'll be better able to use the technology regardless of platform. And speaking of visual editing software, we can segue into my next topic, the data types that GIS can hold. In this context, data types refer to how data are represented in space and or visually in a GIS. Currently, there are only two ways that computers can represent data stored in a GIS, either as a raster format or in a vector format. These are two ways that computers demonstrate the extent, area, or location for which a specific observation is valid. However, the observations associated with that vector or raster can themselves be a wide variety of different data types, things like integers, floats, text, Boolean, etc. The important thing to remember, though, is that how you store data in your GIS as either rasters or vectors influences how you manage those data and what questions you can ask of them. But what are rasters and vectors? In a computer, a raster is like a giant sheet made up of tiny little boxes that store data. So when you zoom up close to a raster dataset, you see pixels that represent a designated area where an observation is valid. In other words, one pixel represents one area and a measurement for some quality in that area. Therefore, when you do any manipulation to a dataset stored in this way, you usually use the whole raster. Relating this back to non-data or non-spatial images, it's like when you zoom in on a picture and realize that it's made up of tiny squares. In those cases, each square represents a specific color so that together they can build that specific image. However, rather than build an image, at least in most cases, rasters in a GIS use color to symbolize an attribute, such as whether or not an area was visible, what its density was, what its temperature was, or what its elevation was. This color relates to a specific value to demonstrate how that trait varied over the landscape. Now, what's a vector? These represent a series of specific things, potentially with multiple associated attributes, that exist within a discrete or exact area or place. When doing analysis on data stored in this fashion, you can actually select specific vectors to analyze and use in other tasks. There are also multiple kinds of vectors to represent the different ways that things exist in space. These are things that exist at an exact location, which are represented by points, things that exist over an extension of places, represented by a line, or things that exist over an area, represented by a polygon. Some examples of this are things like roads, rivers, towns, or buildings. Relating this back again to visual editing programs, it's like when you want to add typed text or a specific shape to an image. There's part of the image that is the text or shape and part that is not the text or shape. And by adding that text or shape, you want to maintain the essential legibility and clarity of the edges of what is and is not that text or shape. Using examples from visual manipulation software can help you understand how vector and raster formats work. So play around with some discrete objects in programs like Illustrator or Inkscape to explore creating vectors, and then turn to GIMP or Photoshop to work with rasters. As you play around in those programs, you might start to see how they could be used to do things like georeference images or digitize features, at least in a kind of preliminary way. Georeferencing is when you associate data with a real location, usually by connecting maps or other data with versions that already have accurate spatial information. But if you don't have access to a GIS program, you can actually recreate aspects of this process in any raster-based image manipulation software. For example, let's say you have a hand-drawn map. If you know roughly where it belongs in space, you can import a digital copy of your map into a program like Photoshop, and then stretch, shrink, and move it around until it fits onto a map that already has accurate spatial information. In a GIS, you do this by creating tie points that say, hey, this spot in this image is the same as this spot in this image. However, due to issues with scale and other map properties I won't get into, you can only preserve so much, and there's often a diminishing return rate on tie points. So what you want to do is add the fewest number of points that result in the lowest error between the two images. You can also visually assess the fit by toggling between the two. Once you've got your map spatially referenced in a way that feels accurate enough for your needs, you may want to have just one piece of that map, like a river or a building, be its own separate thing. That way, you can add additional information about it to your GIS, such as its name, its length, or its height. Doing that is part of the digitization process. Digitization can describe a lot of different things, but in this case, it describes converting something static from a map into something that we can alter in the GIS, like a vector. Digitization can also include things like converting non-digital items, such as other maps or photographs, into digital versions. Both in a GIS and in visual manipulation software, turning something into a vector involves tracing the component using a specific vector type, usually composed of small continuous segments or standard shapes. This allows you to then manipulate the vector on its own without affecting the other parts of the raster that aren't related to it. If you do this in a GIS, you can then add attribute information for that specific vector. There's a lot more to these two concepts, but I hope this gives you an idea of the importance of learning the underlying principles of GIS. These concepts can help you be a better and more thoughtful user, as well as better at troubleshooting when things go wrong. They also help you understand what can be done using this method and technique, as well as the concepts that allow you to do it, even if you might not know which buttons to push just yet. Now that you know what GIS stands for, the two basic data types, and have a brief introduction to georeferencing and digitization, I hope you feel more confident in exploring other videos. Check out our curated playlist to learn more about how to do specific tasks, as well as see some cool applications of GIS in archaeology. Or check out our other Alexandria Archive Institute /Open Context videos to learn more about finding reliable maps online or things like data citation to make sure that you can use someone else's map, GIS, or data.